Alright, graphs on the complex plane, so on the argand diagram. What we're looking at, this is the last bit of our complex numbers. Alright, so often it's helpful to think about what the Cartesian form of the equation would be. So, for example, if we've got something like that you want to say graph Z, where the real part of Z is equal to 6, it's often think about what the equivalent in Cartesian form would be, and the real part's on the x-axis, so that's equivalent to x equals 6, which of course is a vertical line going through 6 on the x-axis. And so similarly, something like Z, where the imaginary part of Z, say, is twice the real part of Z. And if you think about that in Cartesian form, that's equivalent to y equals 2x. And of course the imaginary part's on the vertical axis, the y-axis, the real part is on, the real part is on the x-axis. Alright, so it's often easier for us when we're graphing something to get the Cartesian form and use the Cartesian form to draw the graph. Alright, got all of that? Alright, so let's have a look at a more complicated example. So we're going to sketch the set of Z where the magnitude of Z minus 1 is equal to 2. Alright, so to do this, what we're going to do is we're going to adjust this and put it in Cartesian form. So first of all we need to do something with this Z, because remember the Z is a complex number, so there's a real part and an imaginary part. So if we let Z equal x plus yi, so x and y is what we're used to in our Cartesian form, and then we put that in here. So the magnitude of Z minus 1 equals 2. Well, if we're replacing Z by x plus yi,
Get to say here. I'm only there for everything.
It's my only time of the week, I won't.
Oh, right, okay.
All right, so magnitude of a complex number is the real part squared plus the imaginary part squared the square root of, yes? So that's what we do here. So it's square root of. The real part, well, it's x and minus 1. So x minus 1 squared. Plus the imaginary part, which is just y squared. That equals 2. And to get rid of that square root, I would square both sides. X minus 1 squared plus y squared equals 4. And that is a circle. Of course it's a circle. Right, so that's a circle. So you can see up here, looking at this, what you've got here, in Cartesian form, far more recognisable as a circle than this up here is. So, circle, centre, 1, 0, radius 4, radius 2. So when we go to sketch that, this is what we're sketching, so we've got to put it on an argand diagram. Alright, so real part, imaginary part. Alright, and then we know the centre's here, we know the radius is 2, so we go 2 to the right, 2 to the left, 2 up, 2 down, gives us 4 points, and so if you get your scale right, you get a circle, not an egg.
Like the y intercepts?
You have to, and not necessarily, you just have to have points that you know about. So we know about these 2 points here, we know about these 2 points here, so that's enough to know where the circle goes. If you're specific, huh?
You have to label them?
Well, you probably shouldn't you? Yes, you should label them.
But how do you...
Okay. How do we label them? Just the same way, 1, negative 2.
Yeah.
1, 2, labelled the same way.
Yeah.
You know, the 1 is the real part, 2 is the imaginary part. Right, because we've labelled these as our real and imaginary parts, we've already made that adjustment, so that's what these numbers here, they all represent the real and the imaginary part. All right. Another exam. A few examples got this morning. All right, the next one. Set of z, that's the magnitude of z minus 2 is equal to magnitude of z minus plus I.
What is that? Is that minus 1 plus I?
Yeah, plus I, that should be a curved bracket there. Curved bracket there, shouldn't it? And then that there, yes. All right, so if we use the same technique as we did before, to change it from this form to Cartesian, we do the same thing, we let z equal x plus y I. Now this z and this z, they're the same z's. So if you've got this complex number, you take 2, find the magnitude of it, is the same. If you had the complex number, you took that from it and found the magnitude. So it's the same. It's the same complex number set. So x plus y I minus 2 is the magnitude of x plus y I minus 1 plus I. Magnitudes of complex numbers, as we did just before, square root of the real part squared plus the imaginary part squared. So over here the real part is the x and the minus 2. Square that, y squared. Alright, on the right hand side, just be careful with your signs. Alright, with this minus out there, when I put the minus in, it's minus 1 minus I. So the real part is the x and the minus 1. The imaginary is the y and negative 1.
Oh, 1.
1, right? The I tells us it's the imaginary part. How many? Negative 1 of them. All right. To get rid of the square roots, we would square both sides. All right, now what? Any suggestions? Expand, yep. X squared minus 4x plus 4 plus y squared equals x squared minus 2x plus 1 plus y squared minus 2y plus 1. Then cancel, collect like terms. The x squared's going to go when we take x squared from both sides. The y squared's going to go when we take y from both sides. Then what I'm going to do is, because now y only exists on the right, what I'm going to do is move all the x's over here to and the numbers. So these things here, I'm going to move them across by adding or subtracting, whatever we need to do. I'll just write it all out before, so I've already got the minus 4x plus 4 there. And then when I bring this over by adding 2x, taking 1, then I move this 1 across by taking 1 and leave the minus 2y there. Yes? Alright, so when I neaten this up, I've now got minus 2x plus 2 equals minus 2y. Last step here is to divide by negative 2. And then I get x plus 1 equals y.
X minus 1.
Minus 1, thank you. X minus 1 equals y. Alright, so now Cartesian form. You know how to deal with that quite easily. Compare that to, alright, part of z's there, the imaginary part of z's here. X minus 1, I believe, would go like that. I told you this was going to be fun. Okay, now there's other things that we can do as well with complex numbers that we don't necessarily do with our Cartesian that we've been used to, because we have polar form of a complex number, so then we have argument involved as well. So, we can draw things that are called rays. So here we go. Example here. Sketch. Arg Z, capital Arg Z equals pi on 3. Alright, so the question is, what do we do here? Arg Z is pi on 3. Pi on 3 we know is an angle. We always measure our angles from the positive real x-axis, or real axis in this case, in the anti-clockwise direction. So essentially this then is a line that goes like this, where the angle between the positive x-axis and up here is pi on 3. So here's the wrong one. Real part of Z, imaginary part of Z. All right. Okay. So certainly if we go up there and that's pi on 3. Question is though, what about, often lines go forever, what about down here? Is that part of it or is that not part of it? What do you think? Well, when you think about it, we measure our angle in that direction, that's pi on 3. If I come around here, because arg is negative pi to pi, to get to this, if I continue down here to get to there, I've got to go negative 2 pi on 3, don't I? So that's not included, so that's where a ray is. Now, other thing about this is this point here at the origin is also not included. And that's a technical reason. And the technical reason is that the angle, there's no definitive angle, definitive meaning only one angle that describes that origin. So all of these points on this line, if you turn around, you're turning pi on 3. But for the origin, you could turn any angle. So, technical reason, it's not included. Alright, so what have we got? So this defines a ray which is a line, but it doesn't, ray doesn't continue both ways, it only continues one way.
Can you explain why it didn't continue the other way again?
Alright, so to continue the other way, if I went down here,
Yeah.
to get to this, from here, you've got to turn around that. And that's negative 2 pi on 3. That angle.
Yeah. Oh, so it's not pi on 3.
So it's not pi on 3, is it? It's related to pi on 3, but it's not pi on 3. So the angle that you turn to get to the point, the angle that you turn from the real axis is pi on 3. So you can only get
you wouldn't
things
turn negative pi on 3 either.
No, because it's not, doesn't say negative, does it? It only says positive. So we can only turn pi on 3, and if we turn pi on 3, we're facing in that direction, aren't we? So anything along there where we're facing fits into this. Yeah, that's 180 degrees or pi the opposite direction, but in terms of our definition for arc, to get to there, we've got to go negative 2 pi on 3, don't we? So that's not included. Get rid of it. Defines a ray or line. It makes an angle of pi on 3 with positive real axis measured in the anti-clockwise direction.
So with that circle thing, like in the centre, would you just have to draw that?
Yeah, just draw a circle there. So the origin, so note the origin is not included. Because, what have I written here? Because it is not unique. Oh, there you go. That's better than what I said before. So it's not unique to arc Z equals pi on 3. So on this red line, the only way you can get to those is if you turn around pi on 3. But the origin, you could get to the origin in many different ways. If I was standing at the origin, right, these points here that are pi on 3, the only way I can get to see them is pi on 3, but I'm at the origin. But the origin, I can turn anywhere and I'm still at the origin. So it's not unique. So therefore, technical reason, we don't include it. All right. Now, of course we can shift that around all over the place if we want to. So if we shift that around, I'll just put that one down here. If we shift that around, for example, so example, e.g., sketch arg Z plus 3 equals negative pi on 3. So what do you think this plus 3 does? Translation to the left, yeah? So you get translation to the left. 3. So we're starting here. We could have, there could be an imaginary component which would translate up or down. Then what? The angle is negative pi on 3. So if we're standing here at negative 3, facing all to the positive real, and negative pi on 3 I need to turn down clockwise, yep. So from here, and that angle there is negative pi on 3. This is an interesting one. All right, so far we've just had lines. First line was a circular line nonetheless. Others were straight lines, but we can have regions as well.
Do we have to write out that whole thing?
Okay?
Do we have to write that whole paragraph that you did?
No.
We don't have to write that. do we?
No. I just put that for when you go back later.
Right.
If you want, you can. If you forget, but I know you won't forget. I think you did. You've got something written down explaining what was going on here. So no, you don't have to write that down. All right, so you can have regions. This looks like this one. So sketch argz is less than or equal to, less than or equal to pi 3. So when we're looking at this, arg means the angle, yep. So the angle part of this complex number, anything that's less than or equal to pi on 3. So any of those. So let's have a look and think what's going on. So here's our real part of Z. Here's our imaginary part of Z. And we've got no translations, so it's there. Pi on 3 is there. And we're interested in any angle that's less than that. So any angle that's less than that would be around this way. Now, how far do I go? Arg.
To negative pi.
So it's negative pi to, square bracket pi, isn't it? It's around to negative pi. But not included, is it? So if it's not included, what sort of line would I put? A dashed line. Alright, so the dashed line, not included. Here we've got less than or equal to pi on 3, so that's why I've got a solid line there, because it's equals as well. Alright, normally what we would do is we would shade like that, and then we'll go so that's my region I require. So any complex number in here, the angle to it is less than or equal to pi on 3. One more example.
Is this a long example?
Yep. It's a long example. Right to rub that off. All right. Last example.
What does that say?
Locus. All right. So here we go. It says, describe the locus defined by. Now, the word describe doesn't necessarily, in English it means use some words. In maths, we could use an equation. To describe. Alright, so y equals 2x describes a set of points and the relationship between them. Locus, what's locus? Locus is just a set of points. So y equals 2x describes a locus. It's the set of points on the graph. All right. So what does it mean? What does all that mean? It means find a Cartesian equation. It tells us about this. So if we find a Cartesian equation that tells us about this, then
So this is just what we were doing at the start.
same as what we did at the start, yep. So let z equal x plus yi. And so we've got the magnitude of x plus yi plus 3 equals twice the magnitude of x plus yi minus I. And now we do exactly like what we did earlier on. So square root of the real part, x plus 3 squared plus y squared equals twice the square root of the real part, which is just x, and the imaginary part, y minus 1. And then follow through a whole bunch of algebra. So we got x plus 3 squared plus y squared. If we square both sides, 4 lots of x squared plus y minus 1 squared. Let's put those square brackets in there to remind us that all of this here is being multiplied by the 4. Everything under that square root. Expand, collect like terms, good idea. Alright, so x squared plus 6x plus 9 plus y squared equals 4 lots of x squared plus y squared minus 2y plus 1. Let's multiply that 4 in there. Before we get too far. Whoops, 8y plus 4. Right, let's collect some like terms, shall we? I'm going to move all of that stuff over here first and then have a look and see what we've got. Alright, so I've got x squared that I've got to take away. So that I'll now have 3 lots of x squared. I've got 6x that I've got to take away. And there's no x's there already, so I've got to take 6 of them. I've got a 9 that I've got to take away. So there's a 4 on the end here. I'll go minus 5 after I've taken 9. And the last thing that I've got to do is take away y squared. So I've got 4 of them there. If I've taken 1 away, I've now got 3. And the minus 8y. All right. Who's got any ideas? Anyone? exactly, complete the square. So what we're going to do here is, I'll leave that at 0 at the moment. I'm going to split those up into those two bits. I'm going to take 3 out as a common factor to leave x squared minus 2x. And I'm going to complete the square with that stuff. I'm going to take the 3 out as a common factor from the y stuff. Minus 8 over 3y. And I'm going to complete the square with those things. Alright, so next line down, x minus 1 squared. So on that expansion I get plus 1 here, so you put that in extra, I've got a minus 1 down here. Similar with my y stuff. So I've got y, going to halve that, which would be minus 4/3. And when I square that, I get 16 on 9. So to keep it balanced, I've got to take 16 on 9. And I've got all of that stuff. So I've got minus 16 on 9, minus 5 times 45 on 9, minus 9 on 9, which is minus a lot on 9. Except I've made an error. Who can tell me what my error is that I have made?
Is it meant to be 4 on 3?
That's meant to be 4 on 3. Here I've made the error here with both of those numbers. What have I forgotten to do?
You forgot to times them by 3.
Forgot to times them by 3 because all of that gets times by 3. Same as this. So yeah, you've got to be careful. Yeah. Alright, so plus 1 there, but then when we times it by 3, so we've got to take 3. Then other end, oops, this one here. Don't need that 45 then. This one here. Again, when I square that, I get 16 on 9, but then I times it by 3, which is 16 on 3. Alright, so minus 16 on 3, minus 15 on 3, minus 9 on 3 is minus 3140. Alright. Now what?
No, we just have to describe it.
Any ideas?
Plus the 40 over 3.
Plus the 40 over 3. Alright, let's plus the 40 over 3. 40 over 3 equals 3 x minus 1 squared plus 3 y minus 4/3 squared.
And then divide by 3.
Then divide by 3. Yep, we don't want these 3's here. We need them over there. So divide everything by 3. I've got 40 over 9 equals x minus 1 squared plus y minus 4/3 squared. And that is a circle, centre at 1 and 4/3 what? 4/3 I. Right, so that's or if you like, you don't have to write it in coordinate form, you can write it centre at 1 plus 4/3 I. And radius, to get the radius from this we
Square root.
which would be
Square root. 4.
4 goes into there 10 times, so 2 root 10. The square root of 9 is just 3. Alright. Anything about that? That's pretty complicated, that last one. It's about as complicated as it gets.
Oh, nice.
Alright. Set 8, whatever that is, it's the last one.